Hi class, welcome back to multivariable calculus. In this lecture, we're going to be looking at both vector fields and flow of vector fields. So vector fields have many physical applications. So think about physics and the gravitational field. So anytime you're dealing with, say, force fields, we can draw out those fields over space and show their strength. So we can show the strength of, say, the force of gravity from a certain point drawn out over a field. So, for example, the closer you get to the sun, the stronger its gravitational pull is. And so if you're drawing the magnitude and the length of a vector is its magnitude. So the longer that arrow is, you're showing the stronger the pull, the force, the attraction of gravity is. So as you get closer and closer to that center of mass, the longer those arrows become, and they're all pointing towards the center of mass because that's where gravity is pulling. That's where where all the vectors would be pointed. We can model fluid flow using vector fields. We can look at the flow of vector fields of magnets, dipoles. And so there's a lot of really useful physical applications here. So let's get started, and we'll have a few different exercises and examples that we're going to go through together. So beginning here, let's look at a vector field on R squared. So those are the real numbers squared. That's supposed to be like a bolded R. It's a little hard to see there. R by R, for example. So we're looking in two space. So a vector field in two space, if you have a function, and I'm just going to write Fn instead of writing out function fully. So if we have a function f that assigns to each point x and y in our domain D a two-dimensional vector given by a function of x and y. All right, so because we're dealing with vectors here, we are going to have both magnitude and direction. And so similarly, so for example, in two space, you'll have f of x and y, which is a vector. It's going to be some function of x and y for our I hat component, our x component, a different function of x and y to get our j hat. And the way we could write this is we use like this caret symbol here, pxy, comma qxy. And so closing these in the carets show that we're dealing with a vector, whereas the x coordinate here would be our x component, our equation for our x component, our x direction, and this q of x and y will be the equation or the function for our y direction component. And p and q are scalar fields. So now looking in three space, similarly, some function f, vector f, that assigns to each point x, y, z in our domain in 3 space, which we'll just call E. And I'm taking my time writing this out so that when you're watching this, you can write it along with me in your notes without pausing. So in E, a 3D vector f of x, y, and z. So for example, dealing with a vector now in 3 space, we're going to have 3 different scalar functions. So p of x, y, and z would give us our I hat. Q of x, y, and z would be j hat coefficient plus r of x, y, and z k hat. So once again, we could look at this as, we could write it as in this vector notation. P, x, y, z is our I hat coefficient. Q, x, y, z is our y or j hat coefficient. And r of x, y, and z is our k hat coefficient. So it would look like that. And P, Q, and R are, of course, scalar fields. So now let's go through a plotting example. And we are going to sketch this vector field f of x and y is equal to minus y I hat plus x j hat. So what we're going to do is we're going to look at some x and y coordinates that we're going to plug into our function. F of x and y, and we're going to plot them. So the x and y coordinates I've already plotted ahead of time, but let's just go through. So say we had 1 and 0 for our x and y. So let's start at this point right here. And so if we plugged in 1 for x, that would give us 1 j hat. And then if we plugged in 0 for y, that would give us 0 I hat. And so our direction is going to be 0, 1 for our vector field. And so from 1, 0, okay, this is the point we're starting at, the vector field is going to go towards 0, 1. So the tip is going to point at 0, 1 from 1, 0. All right, so now that's our first one. Now for our next one, let's do 2, 2. So if you plugged in 2 for both x and y, we'd end up with minus 2 I hat and 2 j hat. And so if we find our point 2 and 2, our vector is going to point towards minus 2, 2. So if I find now minus 2, 2, so minus 2 and 2. So from 2, 2, we are going to go left 2, 1, 2, and up 2, 1, 2. And so that would bring us to 0, 4. So let's see if I can draw this. So we're going to go to 0, 4. All right, so that's another one. And next, let's look at 3, 0. So if we plug in 3, 0 into our vector field, we get 0, 3 out. So starting at 3, 0, we are going to go 0 in the x, and we're going to go up 3 in the y. So there's that vector. And so you can see this can be a little bit time consuming, but you can start to get an idea, like next time you see minus yi hat plus xj hat, you'll get a sense, you might have a sense of what this vector field might look like. So let's keep it going though. Let's do 0, 1. Okay, so if you input 0, 1, you're going to get -1, 0 out. Okay, so looking at 0, 1, you're going to get -1 and 0. So we're just going to go 1 to the left. Now let's do -2 and 2, and we'll get -2 and -2 out. So if we go to -2 and 2, we're going to go to the left 2 and down 2. And so from here, oh, sorry, -2, 1, 2, there we go, and down 2. That's going to bring us to -4, 0. And then if we do 0, 3, that's going to give us -3, 0. So going to 0, 3, we are going to go 1, 2, 3, and 0. So that'll bring us here to -3, 0. Here we go, or -3, 3. And then we have -1, 0. And if we plug that in, we get 0, -1. So from -1, 0, we have 0, and we go down 1. If you do -2, -2, we get out 2, -2. So at -2, -2, we're going to go 2 to the right and 2 down. And so we're down here at -4, at 0, -4. Okay, let's do a few more. Let's do -3, 0. At -3, 0, we get 0, -3. Okay, so we're just going to go down 3. You can start to see the shape taking form. And then let's do 0, -1. And so we get 1, 0 out. Okay, so we'll go 1 to the right. And we'll do 2, -2. And then we'll get 2, 2 out. 2, -2. And we're going to go over 2 and up 2 to 4, 0. All right, one more. 0, -3. And that'll give us 3, 0 out. So if you do 0, -3, and then we're just going to go 3 to the right. Okay, so what it looks like is what if we went around and we drew, say, a unit circle in here. Let's draw a unit circle of radius 1, and then we'll do a circle of radius 2 would bring us around here, and a circle of radius 3 would trace us around here. So you're seeing a bullseye, and it looks like each arrow is tangent to a circle with its center at the origin, right? You can see that. And so this vector field gives us this circular field with each arrow tangent to the origin, and the magnitude of the arrows are getting greater as you move outward, away from the center. So let's try something. Let us take the dot product of x, vector x, equals xi hat plus yj hat with our vector field, f of x and y. Okay, so let's see what happens. Let's do x, vector x dotted with f of x and y. So this is going to give us x I hat plus y j hat, that's vector x, dotted with minus y I hat plus x j hat. And that is going to give us minus xy plus yx. Minus xy plus yx is 0. And so if we have the dot product, if we have two vectors that we're taking the dot product between, and the dot product is equal to 0, that tells us the angle, because we're between the two vectors, is going to be 90 degrees or perpendicular. So we can conclude here that, and these three dots, that's just the therefore symbol if you're doing logic or proofs. F of x and y is perpendicular to x. Okay, which you might see considering in the x direction you're going x for the first one, and the other one you're going minus y, right? So they're going to be at right angles. And so these two are perpendicular and also tangent to the circle. So if we were to take, say, the magnitude of vector x, that's going to be the square root of x squared plus y squared, right? And so, in other words, r squared equals x squared plus y squared. Okay, so that is the equation of a circle. Let's try one more. What if we took the magnitude of our vector field, f? Well, that is going to be equal to the square root of minus y squared plus x squared. And so that means that's the same thing as the square root of x squared plus y squared. So the magnitude of our vector field f is equal to the magnitude of x. Okay, which they both are just x, y's. Okay, so, and we're just doing one x in the I hat direction, one y in the j hat, and we're flipping it for the vector field. And so this magnitude here is the radius of the circle. And you see that in our graph here, because if you look at this unit circle here, we have each one of these vectors is a magnitude of 1 going around the unit circle. Now, if you look at r equals 3, the radius here, well, the magnitude of each one of these vectors is 3. So that's all we were looking at. Now, what I'm going to do is I want to show you, I want to look at, one second, I want to look at Academo with you. All right, so in Academo, you can plot 2D vector fields. And I have the link for this up on our Moodle site. And right here, what we're looking at is x plus y for the I hat component and x plus y for the j hat component. And what you see here, and C and D, these coefficients, are just 1. And so what you see here is you have, we're moving away from x equals minus y. And we are going, our vector magnitude is increasing as we move away from that equation, that line here. You can see that line, that blank. And the further you get away from it, all these vectors are perpendicular to y equals minus x. And so that's what this vector field looks like. But I want to show you a couple others. Let's look at if our I hat component was minus y and our j hat component was x. So this is what we were looking at. This is what we plotted together. All right, and so you can see that the magnitude of the vector is equal to the radius of the circle. So as we move further away, the magnitude of the vectors get larger and larger and larger. So that's also shown that the strength of the field is getting greater and greater and greater the further we move from the center here, is what this is showing. So let's look at another one. Let's look at y for our I hat component and sine x for our j hat component. Okay, and so we're also seeing, similar, we're also seeing a vector field. And you can also notice the equation of the vector field is that we're going around counterclockwise. And so trying a few others, let's do natural log. Let's do the natural log of 1 plus y squared. And the natural log of 1 plus x squared. This isn't working. Log. There we go. Okay. And so now you can see what this one looks like, and definitely play with this. In 1 second, I got it. I'll review the last one too. So definitely play with this and use it as a tool while you're doing your homework. So try plotting by hand and also verify in Academo. So let me try the y sine x one again, because that one didn't update when I did it. There we go. Okay, so you can see the sine wave here and the magnitude of the vector field. The vectors are getting larger as you move away. Okay, so let's move on. And you can also do these in 3 dimensions as well. So let's suppose an electrical charge Q is located at the origin. According to Coulomb's law, the electrical force F exerted by this charge on a charge located at point xyz with position vector x is xyz is given as follows, and that is F, vector F is equal to epsilon Q, little q, big Q, divided by the magnitude of vector x cubed. And this is going to be in the x direction, is what that's showing. So we're looking at 2 charges, a little charge and a big charge. So looking at comparing 2 different objects here. And this epsilon is just a constant, so don't worry about that. And so if you have like charges between the 2, then little q and big Q will have the same sign for like charges. And if you multiply the same by the same, a positive by a positive, or a negative times a negative, you get a positive value, so that's greater than 0. And so these would be repulsive forces. If you have unlike charges, so in that case, we'll have a different sign for each charge. So it'd be a negative times a positive or a positive times a negative. So little q times big Q is going to be less than 0. So it'll be negative, and those would be attractive charges, or attractive force. So if you have two charges that are different, say like the north side of a magnet versus compared to the south side, then when you put those together, then they attract. If you have a north with a north, a like with a like, they're going to repulse, and you're going to feel that resistance, and they're going to be pushing each other away. So usually this is written as a force per unit charge. So another way we look at this is force per unit charge. This equation is all usually written. And we call that E, which is the electric field. Vector E is the electric field. And per unit charge would be 1 over little q f. So we're just dividing through by little q. And so you often see it written as epsilon big Q over the magnitude of our position cubed in the position vector direction. And this, you'll find, looks very, very similar to the force of gravity, to the field force of gravity. And what we're doing here is we're just looking at an example of a vector field that we use a lot in physics, so looking at the electrical force or the electric field. So I just wanted to show you that as an example there, and we're going to keep going with another. So now looking at gradient fields. And so gradient fields in 2 space are defined as follows. So the gradient of f is going to be the partial derivative of the x component. So that'll give us our I hat piece, coefficient, and then the partial derivative with respect to y. So it's gradient as we have been using gradient, nothing different there. And similarly, on our cubed in 3 space, the gradient is going to be a function of f of y, x, y, and z. And so we have to take the partial derivative with respect to x for the I hat piece, y, the j hat piece, and z for the k hat piece. And just remember that these are subscripts here, these x, at, y, and z's, those are subscripts. And that's the same thing as, for example, f subscript x is equal to del f over del x, okay, with respect to x. That's all that means. Now let's find the gradient vector field of the following. And we're going to look at f of x and y is equal to x squared y minus y cubed. All right, so let's find it. So the gradient is going to be del f over del x I hat plus del f over del y j hat. And so that's going to give us, so x squared y minus y cubed, the partial derivative of that with respect to x is going to be 2xy. So that's our I hat. And then x squared y minus y cubed with the derivative of that with respect to y is going to be x squared minus 3y squared. And that's going to be our j hat. So let's try to plot this out. Let's sketch what we think this vector field might look like. So if we were to sketch this out, so what happens at 0, 0? Well, at 0, 0, we are going to have 0, right? So we have 0, 0 at the origin. And another thing that we'll notice is that, so if we went through and plotted the level curves, it looked something like a saddle, this function. Okay, so I'm just going to sketch this out, and then we're going to look at it in CalcPlot 3D. So we have a saddle, and it'll look something like this. And it's going to like max, this would be like 4, minus 4, about minus 4, and about 4 to give you a sense here. Looks something like this, the level curve. So remember, level curves are for z equals some constant, right? And then it would be something like this here. And something like this over here. And similar up here. And like this. Not the best drawing here. Okay, but now we're going to use the gradient field here, the gradient vector field, to look at the direction of flow. And so if we were going to use the gradient field and plug in with our 2xy I hat plus x squared minus 3y squared j hat, so if we were going to go through the whole steps like we did in exercise 30.1, you would find that our vectors would look something like this. And I'm just going to draw a few over here. And the closer these contour lines, these level curves become close to each other, the steeper the gradient is, right? The gradient tells us something about the slope. So these gradient vectors are perpendicular to the level curves. And the arrows point in the direction of ascent. So it's like climbing uphill. Okay, so this is where you're climbing uphill, the direction these are pointing. So we'd be going higher and higher in elevation here, if you could think of that as a terrain. And then keep going up, and then we'll start to drop down over here. Okay, and then we're dropping down here, we're going up here. And so you can see it's going to be a very wavy surface. So I'm going to actually open up so we can get a look at this surface. All right, so here it is plotted. And if we went from -4 to 4, it'll just zoom out a little. Look very similar still. And so you can see if we looked overhead, we could get y going in the proper direction. All right, so I know it's not going the same way we're looking at, but if we started at y, you notice that we're going up, up, up as we move towards minus y. Okay, so this is the direction of ascent where the arrows were pointing. Okay, so that's going up, and I have this upside down. Let me see if I can rotate it. It's not very easy to rotate. Okay, and so you can sort of see where we got those level curves from, and you could look at the contour diagram, for example.